record. Record, yes. And I will do like this, and hide. Yes, today we will be talking about self-organizing maps, actually the standard specification of it, which is also known as component maps. Then tomorrow we actually will review the backprop and the multi-layer perceptron. So with some details on really the derivative, so the math behind it. Again, so I'm not sure how many of you have learned the small details of perceptron. So even if you did, so it will be kind of a recapitulation. And next week and the week after that, so we will be talking about processing or learning on sequences or time series. And in this module, we will be talking about the way how, a feature-based method. So how to extract features from a signal and a neural network-based approach for processing of time series. And so connected to these three topics, you have three more labs with a deadline basically end of December or before Christmas break. One on self-organizing maps, so we will have a look at the code today. One on MLP, and again looking at the implementation. So it's not the library-based not the API-based programming. And lab 4, so implementation of an entire network architecture, recurrent neural network architecture, which is called echo-state network, based on specifications. So based on actually a research, more or less research article. And the last lab is you can expect that it is most time consuming. Right. You all see me, right? So let's talk today about self-organizing maps. So I will do some writing just in the face. So self-organizing maps. So here, so we start to talk about neural network architecture. So basically, a class of algorithms that are inspired by some biological observations of how, in particular, human cognition is functioning. And it's very important, in my opinion, to bear in mind that it is really a biological inspiration. So, to distinguish between terms biological plausibility and biological inspiration. So, so for example, talking about spiking neural networks, so that's more or less biologically plausible way of defining neural networks. All other network architectures, they are more, at best, are biologically inspired. So they approximate, it's a mathematical approximation of biological processes. So, what is the inspiration, biological inspiration for self-organizing maps? So here, so we have studies in cerebral cortex, of cerebral cortex. cortex, and specifically a study that specific inputs or particular inputs activate certain areas in the brain. So we, well, there are much better visualizations, but so if we have our brain, and so if you have a certain class of concepts, or at least say you have audio input, so then it, well, at least on this level, so it activates certain part in the brain, video or pictures activate other part, etc. And so this process is called the topographical mapping. Topographic mapping. So, but in other words, neurons that deal with closely related information, they are kept close together. So as part, well, it's part of learning, it's part of evolution, but so similar input activates nearby neurons. So this is an observation, and I guess it's kind of well known. And so the idea is that, I mean, again, so I mean, for this type of input, so the neurons they communicate via shorter synaptic connections. For faster processing. So self-organized maps, so they it's a neural architecture that follows the principle of topographic map formation. The neural map follows principle of topographic map formation. Yes. So what does it mean? It means that so that was the inspiration, the overall idea of SOM. So that you arrange mathematical models of neurons in a kind of regular topographic structure. So you have neurons arranged in, well, for example, a grid. So that there is certain structure in the placement of neurons. So this one is a neuron. And then basically the idea is that this, yeah, and all neurons, so they will have two types of connections. So they will have so-called lateral connections, so they will kind of be interconnected with each other. And they will have also connections to an input. So if you have an input here, So and what input is our, for example, feature vector. Feature vector. So I mean, this feature vector will be kind of connected to each of these neurons. So to this. So this is the idea of the architecture. And so the strength of this connection will be defined by a weight vector. So basically V1, V, and so and this is important. So the dimensionality of the weight vector corresponds to the dimensionality of the input. So basically, yeah. So this is the high level idea. And then, so each neuron will compete with other neurons in this whole topology to attract certain type of patterns. Attract certain pattern of input feature activation. So and so saying this, so it brings us to I mean to main distinction of the self-organized map neural network from, for example, neural networks based on backpropagation. So in the backpropagation, we use error-corrected learning approach. So we try to correct errors. So here we use competitive learning. So basically, in error correction, so we adapt the weights of the adapt the weights of the neurons or the neural connections based on the knowledge of the error. So then that's typical for supervised learning. Here we are in unsupervised learning, so we so supervised. So we don't have this indication, and that's why we have competitive learning. So, and as I said, so if we, well, I will not redraw. So I will go back to this illustration over here. So, and this is important. So the idea is that each and every neuron tries to attract certain pattern, the input to itself, and it means that one neuron will be kind of more attractive or more competitive for a given pattern than the others. And this neuron, it will be only one neuron of this kind. So most attractive. Or in other words, it will be a winning neuron. And the idea is that as soon as this neuron is determined, then this neuron performs adjustment of the neural weights, of the connection weights, in its vicinity, in its neighborhood. So, and this strategy is called the winner takes all. So the idea is that you give a pattern X, and only a single neuron will be activated, and this neuron we call a winner. And then, once determined this winner, so it will perform certain actions, instructing other neurons to do something, so to adapt their weights with respect to this pattern. So components of some algorithm. So first, as with all other architectures, we have initialization. Initialization phase. In the initialization phase, so all weights assign random values, small random values, normally taken from normal distribution. And so the second phase of SOM is competition. So for this, each neuron has a so-called discriminant function. The discriminant function. So basically, this discriminant function, so it's computed for each input pattern. So if you have vector X, so it is inputted into this discriminant factor function for neuron I. And later on, so you take a minimum, so to determine a winner, so a minimum over all i's in this Fi. And that will determine a winner. And once winner node is determined, so now you transition into a phase which is called co-operation. So, and in the cooperation phase, it happens several things. Actually, the whole learning happens in the cooperation phase. So what happens is that the winning neuron determines the neighborhood of other neurons that will be excited for this input pattern. So when I say pattern, so it's just a collection of inputs similar with respect to certain measure to a given feature vector. So, but this is kind of the steering rule. So, winner determines the neighborhood. So, neighborhood is a term here. For such neurons. So, and the idea is like this. So, if we have this so neurons, well, now I will put them in some unstructured manner. And for example, this neuron is a winner. So it will. Oops. It will define a neighborhood. So let me see. Within its proximity, where other neurons will be activated on this given pattern. So neighborhood of neurons. And then obviously, so again, so it's quite logical that not all neurons in this neighborhood should react equally to a given input. So farther away nodes should be less affected by this input. So you need somehow a decay function so for this size of the neighborhood. So and that is these three phases of the algorithm. So now we will put some meat on the bones. So first, the discriminant function. Well, discriminant function is nothing more than just calculating a measure of similarity or distance of the weights, the current connection weights of this neuron towards the input and the actual input. So basically, I guess, well, you can choose any measure. Most common measure would be an Euclidean distance. So, or again, so to maybe say or make computations more efficient, you can square the Euclidean distance or avoid computation of a square roots at the end. But d of x is actually a sum x I minus Wi square. So these are this is the input features, and this is I from 1 to G or N. We use N previously. N is dimensionality. Right. So this simple. So I will later on comment about the usage of other functions. So you can, in principle, use even cosine similarity. So I will also talk about binary self-organized math. So basically, when the features are binary, so zeros and ones, and in this case, so you need to change this measure of similarity to a more suitable function. But the idea is very simple. So you always compare the weights of a neuron towards each neuron towards input with the current feature vector, and the closest one with respect to Euclidean distance will win. So in the cooperation phase, so as soon as we found this neuron, so let me just go some more things. So say this one, this neuron won the competition. So its distance, so the distance of its weight. So now, so this is your input. Input, and actually it's like well, directly illustrated. So you have n neurons. If it would be, I mean, if we just think analogously to the vector of multilayer perceptron. So we have input neurons, and then all of them so connected to so they have as many connections to the neuron on this with this topographical structures. So it means that each neuron would have this number of connections. So it will be characterized by weight 1, weight 10. So, and that's what you compare. You always so these are the weights of these connections you learn, and for a given input, so you determine so which one is the closest neuron. And then this lateral connection, so it's like you should imagine it like yet another dimension so for communication between the neurons. But and now, so when we found out the location of this neuron, and this neuron is characterized by its index, so I of x, so index of the neuron. For input x. So it starts to form a neighborhood around it. So and here is a crucial. So so since we have this extra connections, so we can introduce a notion of a distance. So basically, we can define the distance from the winning neuron to any other neuron. So, for example, this distance over here. So if this is node I, this is node J, or neuron J. So our distance S. The distance from I to J, to lateral. While being here, so so one possible question is why this structure? So why lattice? Can it be any other topographical structure? Yes, it can. It can be a line. It can be a 3D structure. It can be well, like a torus, for example. So it really, the only thing that helps maybe is the visualization, better visualization. If you think about it now, so I mean, what we are achieving with this neural architecture is more of dimensionality reduction. So we map all the inputs. I mean, we map patterns, like relative patterns in high-dimensional input into activated neighborhood on a, let's say, a given topological structure. And what you should expect already now, like visually, after this point, that's, for example, say we work with the MNIST images, so written digits 0 to 9. So that zeros will activate mainly region here, but maybe some weird zeros will activate nearby region. While 9 will be located quite close, but not exactly, maybe overlapping with the zeros, etc. So you will see a kind of regions with emerging categories around this structure. And this is very useful. So I mean, t-SNE is good, and well, t-SNE actually is de facto standard, I would say. But SOM has its own power because I mean it's at the end it's all it's neural architecture. And then I will show you some other variants of it. Yeah, but nevertheless, so now we should have means to kind of define this distance between nodes I and G, and so we want to express it mathematically somehow. So what we want essentially, we want to define a function that decreases the strength of influence of this node towards the end of the cluster. So that's kind of the center of the cluster with the winning node will have the most influence for this for the particular pattern, and then it will decay towards the end of this formation.
Just a quick question.
Yes.
So this is more of a visualization way. So if we can classify something visually, or what is the output? Is it the neighborhood? And then in that way we classify it, or
it's a good question. So it can be used for visualization. It can be used without. It can be used on its own for classification purposes without visualization. So visualization is yeah, it's a bonus here. So talking about classification, yeah, since we are talking about it, so let's spend a few moments. The usage So one is really for visualization. So you can, so if you have a map, self-organized map, so a 2D plane, so you will see the concept. And if you have labels, you see, so if you have labels, you will you can color it. So but also, I mean, you could well, coloring essentially is equivalent to assigning a category to each neuron. So what happens is, so you have a +1, +I here, maybe some plus J here. And so on and so forth. How do you do classification? So you have these neurons and in the training phase. So first of all, so you create this structure without any label. So this is unsupervised learning. But then when you are happy, so you run all these 3 phases, and actually, so I will tell about the training procedure. Here, so when the map stabilizes, so you go into the labeling phase. For categorization.
I'm assuming that's an issue that you don't know what to label, right?
Yes. So you have, say, 4 labels, and 1 and M. So in the you take training data, and you run only the how do they call this phase? The soft phase. The competition. So you to determine the winning node. So you determine the winning node, and so you keep track of the labels that keep this node. So you basically do extra bookkeeping. And then there are different strategies. Normally, you just select the most frequent label. So each neuron is then assigned the most frequent label. Where you can also do maybe even KMM per neuron, so that just to see what is the closest one. But then there are different choices. Training data to report labels at winning nodes. So, and then so you have a neuron, and here you have, for example, label 1, the label maybe is 10, label 1. So you say, okay, this one is most likely label 1.
Sorry, a quick question again.
Yeah.
Might be a stupid question, but how do you determine how big the area will be from the starting?
It's a very good question. So it's I mean that's what I stopped with here, and that's where we will continue now. So you need to define this neighborhood. So you need to kind of define how large is the area indeed, and within this area, so you need to be sure that the strength decays, and this is done in the following way. So controlling neighborhood. So you have a function for that, g, which equals e to the power minus s I j squared divided by 2 sigma squared. So this is a Gaussian Gaussian distribution. So if you would plot it, so this one is the distance distance from V9. This one over here, so sigma is size, is a parameter controlling the size of neighborhood. So maybe at this point I will switch now to Python and show it its attack. For that, but again, so is this understandable somehow? I mean, the formulation. So this s is the distance is given, so it's not. I mean, that is something. I mean, you can calculate from one node to another, and so for this again, we are. I mean, it depends on this structure, the topological structure that you choose. So in the lattice, so you assume that you have this x and y, y and x coordinates. So you can have, so you can you give coordinates to each neuron. So say 0, 0. I mean, in Python we start numerating from 0. Let's say that was 0. So then 1, 0, etc. So that's a neuron. Here it's again 0, 1, and so on and so forth. So you can really, so if you hit a neuron here, so you know its coordinates. So, and then I will show you how it's done in the code now. So x, y coordinates, and as such you can compute. So I mean the size of the structure is a parameter, and you can compute basically the distance to all. So and what this function does, so it takes the distance and computes and compute g, which is the decay factor, which actually in this formulation reduces with the farther away you go. So the larger is distance, the smaller will be the value of g, and the decay will be according to Gaussian. Well, it will drop exponentially with the steepness of the drop controlled by the sigma parameter. So, but again, so let's have a look. So you are given a code, and on purpose I separated this part from the main algorithm. So let me see if I yes, no, I can do that. So do you all see? So let's so this is the code from lab 4. So what? So there's some imports. This is our Euclidean distance. Well, actually, here we use square. Maybe I need to. Just to be. Now. So this is the function that computes Euclidean distance. What do we do here? Well, this is some. Not very. So we model a case with 3x3 lattice. So 3x3, so 3 neurons along one axis and 3, so altogether 9 neurons, and the number of features is also 3. So it's 3x3x3, and so here, I mean, that's. I mean, there are different ways you can generate this topology. So here I use mesh grid. So mesh grid creates well, coordinate system. So so, I mean, that we need. So if we determine a winner node, for example, in the middle, so we know that it's coordinate, for example, 1, 1. So we can consult array X to find out the index of the winning node. So what happens next? So I just so we have this sigma. Well, I will tell about sigma decay soon. But maybe this is more important. So this is a kind of input that's not an input. So this is the result of calculation of this distance. Again, just made up for clarity. So you give an input and you compute the Euclidean distance. I mean, in all 9 nodes, and this is the outcome. So in node 0, 0, you have distance 2, then 0, 1 is 1, etc., and so on and so forth. So this so dist. Let me see. So this is the intermediate result for distance calculation. But again, so maybe for the discriminant calculation. And now we calculate, yeah, and here in the next row, we find the minimum. The index, the row and column index of the neuron with the minimum distance. So if you now plot this, BMU, by the way, stands for best matching unit. So let me just. I and here. So if you just type BMU call BMU row and run it, So it's 1, 0, 1. So it's 0, 1. Which is well, I removed it. So what you do next? So you determine this index for the best matching unit, and this X matrix. Let me see. So this is X. So these are all the indexes. So you can in your topology. So what you do here, you compute the distance. So these are this is your Sij. So you square the difference of the first coordinate plus the difference of the second coordinate. Let me show you here. So S, let's spell it out. S-I-J. Oh. Sij, so this is a Euclidean distance. Distance I to J. So it's basically, or maybe, yeah, so it's basically I minus J really sorry for this computing writing. I just want to connect it to the code better. So let's let I the node on topology, and the new and J is the new best matching unit. So they have coordinates x, the u, y, the u, and here we have the index x I, y I. So S B and U, B and U to node I is square root the x. I think it's changed places. I to the mu. I and U. So it's I minus x U square plus y I minus y u square. And so this G is equal e to the minus power minus S I d u squared divided by 2 sigma. So then the square root and basically go off. Yes, and that what it is written here. So you what is computed here. So now It would be interesting to see what the result of this G function is. It is like this. So it has the strongest influence at the winning node at the best matching unit, and then it decays the farther you go from this node. And then, I mean, we are talking about learning, so it's about adaptation. So you have, I mean, we are working with scenarios with lots of data, and I mean, neural networks. So they almost like never are trained from a single shot, so to say. So this size of the neighborhood should be adapted. In which way it should be adapted? So maybe in the beginning. So again, think logically. So when you just initialize the network, so you want to propagate the influence of or even of a single pattern quite far away. But then the farther you go in the training process, so with number of iterations, so you want to shrink this neighborhood, so only fewer nodes or nodes in the smaller neighborhoods become reactive on a given pattern, and this is captured by saying that this parameter here depends on time, so or on iteration step. So sigma t prime t equals to some initial value for sigma. And again, so that's quite typical in machine learning. So you see this Gaussian distribution very often. So e to the power minus t. So this is the iteration step, and here again. So this is your hyperparameter tau sigma. This is the decay rate. So how fast you shrink the neighborhood with number of iterations. And then again, so that is what actually happens. So if you let me see if where I do have. In the very beginning, so it's like a single activation, so makes the entire network look like this pattern. I mean, to some extent, with the highest the reaction in this best matching unit. And then, I mean, you give another pattern. So again, so you will have this very kind of not precise borders between clusters. So they start to emerge, but they start to emerge the more iterations you do. So when you kind of make the borders between the clusters crisper with respect to the best matching unit. So. Yes, that's it. Yes, this is the neighborhood parameter. But now, so what's next? We now know how to define the factor, the influence factor. So for a given neuron, what we do now, we define. We go into the adaptation phase. Where we reduce the weight on your map with respect to this influence. So what you do here, so you compute the difference in weight as, or you take the current input, and so your feature vectors. let me rewrite it in vector form, right? Minus current weights. So you do reduction based on this G coefficient, and further, so you introduce a learning rate. So this is a learning rate. So even basically the best matching unit wouldn't look exactly as the pattern as the current inputs for which it won the competition. So and in this way, so we adapt the weights across the topology. The last thing remains to say that this learning rate also changes with time according to the same principle. So equals some initial starting learning rate E T and then tau. So this is again the decay rate. So and that is more or less it with respect to specification of the protocol. So your SOM is determined by the following factor parameters. The sigma 0 and tau sigma and 0 and tau. So this is how you parameterize. So you start with you start with these parameters, and you first run and you run this network for a very large number of iterations, like several hundred. So obviously in your lab, so maybe you will see basically so how much time consuming it is. So the larger map you choose, so the slower process, learning process, convergence process is. So, but again, what you can do, you can work with some smaller configuration to get some first indication. So here is self-organizing maps again. So this is the classical structure of it, which was suggested by Finnish researcher Koponen. And after that, there were different variants of SOM. One of the interesting variants, again, so I mentioned it last time, so connect to this group in Australia I'm we're collaborating with. So they suggested a so-called growing SOM. So what is the limitation again? It was really interesting architecture, neural architecture to begin with, but obviously, I mean, since you kind of rigidly define the topology, so that's one of the limiting factors. So, I mean, the structure of your data can be much more complex to be projected on a 2D structure, for example, of a given size. What they suggested to the growing SOM, so other variants, so for example, growing SOM. Well, actually, they didn't change any the assumption of a 2D plane, but sorry, I said it incorrectly. So that's another problem with the SOM. About the the fixed number of dimensions. But one problem is, for example, to choose correct dimensionality of this lattice. So should it be like 20 by 20, 40 by 40? Who knows? For some small cases, you don't need very large maps. But again, it's very hard to kind of select this parameter. So what they suggested in growing SOM, again, I will not go into details, but you can find it in literature. So you start with a very small topology. Topology. So basically, the 4 nodes, or even a single node, arranged in this structure. So 0, 0, 0, 1, 1, etc. So you run SOM according to the previous algorithm. So but then you evaluate. You evaluate the quality of this structure. So you basically define a threshold on the mismatch, so the error. So you see how this one node. So it will often be it will often become best matching union for many patterns. But for some patterns, it will, for example, the distance will be way too small. I mean, the similarity will be way too small. And they define the threshold for quality. Of quality of that matching union. So if you want, but you are under threshold with respect to this measure, so you keep the statistics of this, and when you reach the threshold that, well, this node is attracts many scrap input, it means that you need to do something. So you need to enter the growing phase. In the growing phase, you add new nodes. So you still assume that you're on a lattice, but your shape of the nodes is not determined, so to say. So this is your initial nodes, but then, so for example, this one is faulty, or attracts too many. So it becomes very unspecific. It attracts many records, and most of them with very low similarity. So what you do, so you split the weights. So you add nodes. I mean, on the backend places of lattice. So you still work on the lattice. You split the weights to these two nodes, and you keep working on SOM. And in this way, so your topology, I mean, it can, the actual topology after training can take very interesting shapes. So it may, for example, form a star, or you will see some branches, so that one category really kind of being prolongated along a certain dimension, etc. Again, it's interesting from the point of view of data analytics, so to understand your data. Next, again, so we further evolution of SOM. What you can do, you can use it as kind of in the continual learning scenario. So I will not write anything. So again, so if you're interested, so you can find this information in the literature. So what happens here? So when you train a network, So it becomes kind of stable for a given distribution of input patterns. But in real world, so there is this concept of or phenomena of concept drift. So it means that the phenomena that you observe, so it changes with time. I mean, the typical example, so you create a model for some part of machinery, which wears out, and then they start to produce a different telemetry. And this new data, so it doesn't, well, it fits to the previous model, but fits badly. So you probably see, and this can be noticed by, for example, again, by similarity or the degree of similarity to the best matching unit. So you see that, for example, if previously it was like a node with very strong attraction, then it starts to decay with time. So with respect to kind of distance measured to a new input pattern. What you could do in this case, so you could decide, so if something happens, and you can start growing new structures. So there is a phase where you can say, again, on this example, say in a stable, so after training is finished, so this square node start to weakly attract input, and then you say, well, but so now we need to grow a new structure, new SOM, and for this what you do, you aggregate weights from the neighboring nodes. You create a kind of a new node so that you don't start to create the topology from scratch, but from some say average weight of the nodes in the neighborhood. So you make it say a single node, and you start developing. So you start adapting to this new signal. So you start, and then if you keep this versions of different SOMs, so you can see how this phenomena transformed in time. But again, so that algorithm is the kind of first of all, it's not mainstream, and it's quite complicated to give it as part of the course. Last thing I promise you, I want to say is the type of input pattern. So there are cases when your input pattern can be binary. So there are different ways to do that. I mean, in the simplest case, again, you have MNIST, and then you can make it black and white. So what I would have this binary input. But for binary SOM, so then it's a challenge. So you need to adapt. So you don't have real numbers. And why would you don't want to have real numbers? Because maybe you want to have, say, FPGA implementation of this. So you don't, so very fast kind of self-organizing architecture. And in this case, you in binary SOM, so a discriminant function is Hamming distance. For the starters, so it's basically how many positions disagree. I mean, in the binarized weight and in the binarized input. But then also when it comes to updating, so for example, if a position, so of certain weight was 1 and the new position is 1, so no, I mean, you don't change. But if the new position is 0, so I mean, the risk with this kind of networks, that is also kind of similar to this binarized perceptrons, binarized backprop network. So I mean, just flipping the weights can result in unstable behavior. So what you do here, you introduce some probabilistic update. So when you are not sure which weight to update, so you toss a coin basically. And finally, I just want to show you, and with this I want to finish this class. I want to show you something which is called elastic maps. Yeah, here I think it's elastic map. That's a kind of interesting thing. It's also used for visualization, and it was created. I met this person accidentally, and apparently, so while talking, we discovered that we had same supervisor. I mean, I had it for him for master thesis, and he had it for PhD. But here, the idea is that they applied. So it's pretty much similar to SOM. But instead of kind of rigidly defining the topology as just something given arranged on certain coordinate system, they treat these neurons as nodes connected by springs of certain with certain elasticity. And what you do, so it's like so your topology becomes kind of a physical system which stretches, and the way how it stretches is basically the weight that you try to learn. So it's very similar, but it creates really a cool visualization. So again, it's not a mainstream, but I hope so. If you're interested, then at least you have you heard from me that there are such things as elastic maps, and there are other variants of SOM. So if you are curious, you can find them. Okay, any questions? Okay, then well, you will experiment more in lab 3 with this, lab 4 with this. Thank you.
Ja. Hade du någon uppgivning på sidan? Jag såg det i Canvas.
Ja, de heter Seminar New. See you next time in Zoom. Bye.